Yeah, our term project will be modeling a polymer system using method with change statistical associated fluid term pure equation of state. My name is Abdurrahman, and I have my colleague Ahtisham.
White stage.
Okay, in the table of content, first we'll start with the introduction, methodology, resultant discussion, conclusion, and future plans, and multiple choice question. So we'll start with the literature review. Our paper is modeling the polymer system using PCCRT, which is the peer-to-peer chain static associated fluid theory, equation of state, and the thing that was mentioned is doing thermodynamic in polymer is very difficult, and the most to keep in mind the phase equilibrium of polymer system, which often involve high pressure liquid-liquid mixture, or as well favor liquid mixture at lower pressure. So in the paper, they compare between PCCFT and SAFT and see some of them. So the equation that we use is applied to model phase behavior of binary and tertiary mixture of polymer, solvent, and gases. Using constant binary interaction parameters. So the equation of state gives good correlation of the appropriate phase behavior over wide temperature range. Also, for designing and optimizing the polymer production plant, the knowledge of phase equilibrium is requested. Difficulties in modeling thermodynamic that you need to put in mind. First, polymer systems are highly density dependent, where Gibbs free energy model usually fails. And second thing is less experimental data available for polymer. Physical-based equation of state derived by applying the principle of statics mechanism, and lastly comparing with the Ingrid-Benson model for favor liquid equilibrium for binary system is given to confirm the good performance of suggested equation of state. So my colleague Ahtisham will go through this.
In the methodology part, for using this thermodynamic model of PCSAFT, which is the perturbed chain statistical associative fluid theory equation of state. So we need different model parameters, which is the segment diameter. Like if there is a molecule in a polymer, so it will be kind of spherical. So there will be some diameter of the sphere. So we need the segment diameter and the chain length for the different segments, and then we need the association energy or the dispersion energy, how the molecules are interacting with each other, with how much energy. So only then we can estimate or model the behavior under different conditions of temperature and pressure. So we have the pure component parameters for the species equation of state for HDP, LDP, polypropylene, polybutene, polyisobutene, and polystyrene. And these are the references how we get these pure component parameters. They are actually found by fitting to the liquid density data. So in the results and discussion part, we have a system of liquid equilibrium. Like we are making a polymer blend, and we have polypropylene plus another solvent, which is actually N-pentane. So there will be a liquid-liquid equilibrium. So we are estimating the liquid-liquid equilibrium under different temperatures with changing the weight fraction of the polypropylene. So you can see that these dots or the solid points are actually the experimental data. So the polymer PCSAFT is correlating well to the experimental data or estimating them well. So this shows us how much is the better accuracy of the thermodynamic model. So next is the system of polypropylene and N-propane solvent. So you can see that for the different temperatures, the polar PV shaft is giving better estimations. Like we are very close to the experimental data as compared to, if I can show you here. Yes. So we have two cases in which we have polyethylene and the high polyethylene with ethylene mixtures at 3 different temperatures. So you can see that one is the polar PV shaft equation of state and the other is the shaft equation of state, which have the different terms or the different calculation method. So you can see that if this is the experimental data and we have the polar PC shaft equation, which is the solid type. So this is correlating well or closely to the experimental data as compared to this. You can tell the dotted line. The dotted line is the shaft. So which is very far away from the experimental data, which shows consistency of our model. As we have told you that this is a improved model, thermodynamic model for modeling the polymer systems. So what is the benefit we can get from this plot or this idea of modeling the polymer systems using thermodynamics? Can anyone tell?
Not doing the experiments,
Yes. And
predict whatever like.
some. He's correct, like we don't need to have to do every time the experiment at each different temperature. Like if we already have the estimation for these two temperatures, we can have the thermodynamic model. Also, there is a big cost associated with the experimentation. So every time you are experimenting and you are just spending some money, so you can save the time, energies, and the money for all the experimentation, and you can rely on the better thermodynamic models. So similarly, it is the vapor liquid equilibrium of polyethylene with ethylene binary mixture, and the references are given. So we can see that here at let's say if we are at a high temperature of 155 degrees. So what will be the solubility of polyethylene in ethylene solvent? So we can see that if the pressure is 40 bar, so the polyethylene fraction is higher for the case of the high temperature. So which means the solubility is lower for the ethylene solvent. Now we will try to test our thermodynamic model for the ternary systems or the multi-component systems. Different thermodynamic models, when they change the components on which they were developed, so they fail to model the systems which were not meant for them. Are you getting the idea? Like we make a model according to one certain asymmetric systems or similar systems, but now you are introducing different systems, so there will be deficiencies or weaknesses in the model which will become evident if you change the components. Now in this ternary mixture, we will go for the multi-component mixtures, and we will go for a new kind of system, which is the polymer with the solvent and with the supercritical gas, which is CO2. Actually, in the industry, there are polymerization reactors, and this gas is also used in those reactors for process engineering. So we are changing the temperature and we have the pressure, but as we increase the content of the CO2 in the reactor, so there is different kind of cloud point, or we can call it simply the vapor pressure. So if there is high CO2 content, then there will be more vapor pressure of the ternary system. Similarly for the figure 6. In the conclusions, the thermodynamic estimations of vapor-liquid equilibrium or the cloud point or the liquid-liquid equilibrium from the PCSAP correlates well with the experimental data. We can see that the PCSAP thermodynamic model, which is derived from the perturbation theory, gives consistently better results for different systems like the binary mixture, the ternary mixture, and the physically based equation of state can be extrapolated outside of the regions where they were developed. Like you have made the equation of state and found the parameters within certain range of conditions. But if it has some physical background or basis or some understanding, you can extrapolate it to the higher temperature or lower temperature conditions or different pressures. So also the PC SAF equation state was applied to a three-phase system like the vapor, liquid, liquid equilibrium. So, but I have not said those results here. This is also sometimes the case in the polymerization reactors. So it can also give us the two-phase equilibrium, liquid, liquid, vapor, liquid, and vapor, liquid, liquid. In the way forward or the future plans. With the help of information or the data from this paper, we can model some other industrially relevant polymer systems using this equation of state. And the properties prediction for complex polymer systems can also be done, but still further improvement is needed in this problem. So these improvements can lead us to higher industrial applications of the thermodynamic model for the property estimation. So this is your favorite part of agriculture. So can anyone read this one?
What's the question one?
Yes.
Can you read it?
Yes, you can.
I can't read it from here.
Question one.
Modeling polymer systems using equation of state do require some pure component parameters or
Yes.
not allowed. Okay. So let's say yes, for a fixed CO2 content, if the temperature is increased, then what will happen to the vapor pressure in the cloud?
Increase.
Why it should increase? Because
More
the
vapor.
CO2 is more volatile. If the CO2 content is more increased in the reactor, then the cloud point of vapor pressure will also increase.
Yeah, but pressure is a function of temperature.
Yeah, we will see. Yeah.
Both of them at the same time increase.
Okay, the last question is which equation of state is more accurate for modeling polymer system like Peng Robinson or PC SAT or SAS or SRK?
Also?
From the name, B.
So this is a spin-off of the original SAF equation.
Yeah,
Yeah.
modification.
This is improvement of the
Wow.
SAT.
Okay, thank you very much. Excellent.